Hello fellow problem solvers, so today we're going to be doing IMO 2022 problem number 1. Cool combinatorics problem. Nice if you're getting just ready to do some combinatorics outside of techniques. If you know some of our heuristics, some of the rules we've talked about, problem solving strategies, how to solve problems in general, this is a great problem for you. Try it out at minimum 30 minutes, ideally 92, but not more than 4.5 hours. And now let us begin. So, what do? Let's see. Well, I've changed the problem just a little bit. You see, every country names the character that is doing this thing, and I've named ours the chef, and I said they are doing this operation. So, now, what is happening in the problem? So that's the first step that we should do. Pause, for 5 minutes and read the problem. Try to understand what's happening. Pause now, and what is happening is, okay, we have some process, and I'm saying, okay, so I pick a number k that's less than 2 when I have n coins that are A, n coins that are B, okay, and then this process is happening. So I'm here, I take these three, I move them to this side, and I'm left with this. And now I pick, okay, these 3 coins, they form a chain, I move them on this side, I'm left with this, and then I pick these 4 B coins, move them here, and then it just continues. I'm just moving them at the end again and again. The process sort of goes to infinity and stops, and we must find, okay, find all n and k such that no matter what initial position we have, we are going to get 4 coins of the same, like n coins of the same type at the end, at the beginning of the chain. So here's where I invite you to pause for 3 to 10 minutes and do what? You don't know what the problem's about. How's this like? I mean, you understand the problem, but you don't know what is happening. Why is this happening versus like, how am I even going to begin the problem? What do you do then? You play around with small cases. So please pause now and let's do that. So what happens when we play around is that we have, so for n equals 1, we get, okay, k1 and 2 just work. Doesn't matter what k is, it all works. Now for n equals 2, we see k1 and k4 don't give us what we need, but k equals 2 and 3 do. Now, okay, like, is there something about them being squished in the middle here, right? That the edges don't work, but the middle part does. And what we see for n equals 3 is, okay, k1 and 2, again, do not work. K equals 3, we just enumerate everything, and it seems to work out. Now, k equals 6. How we construct it is like, for k equals 1, we were like just, okay, A and then B, A, B, A, A, B, A, B, and then it would just keep going into itself. For 4, we'd have A, B, A, B, and then it would go B, A, B, A, and then back again, bum, 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 bum. Now for 2, that's not the thing that actually didn't work. Like if we're going to, enumerate stuff out, if we're just set, A, B, A, B, A, B, that's not where we get to a problem. Initially, the problem is the double A and then the double B. That's where the problem lies. So what is that? What does that mean? Well, right, we could just start off from this instead of A, B, A, B. Like that would, like B, A, B, A, B, A would lead us to this, I believe, but we can just start off with this and we get into a cycle. And it doesn't work. So can you from here, maybe just get a hypothesis for what might not work in general? For me, this was like enough amount here. Okay, wait a second. For 4, I'm thinking the numbers for 1 won't work because I'll have, if I have A followed by 4 B's followed by 3 A's, I'll just keep going into this. I mean, in fact, forget about it. Like, let me just start off with 3 A's, 4 B's, and then an A. Now here, for k is equal to 1, 2, and 3, I'll just keep getting back into itself. So what is the first thing that you see? Well, for me, the first thing I saw was, well, if k is less than n, this will not work. Right? If the initial one is n minus 1 A's followed by n B's followed by an A, this thing ain't gonna work. So k less than n does not work out. And that's what we get through playing around and understanding what is it that's happening? Now, we must move on to our hypothesis here. Okay, so the middle one seems to not be working, so I'm assuming k equals 5 shouldn't work either. Like, I don't know yet, but this is just a hypothesis. And if you haven't tried out k equals 5, try it out for about 5 to 10 minutes and see what you get. I'm going to do it here. What I get for k equals 5 is that, in fact, it ends up working out. No matter what like, this is the complement here. Like, if I have, this is just saying if A's and B's interchange signs, like if A is B and B is A, it's this, like I get the same thing if I just switch them around. That's what I mean by complement here and complement here. And I'm enumerating all the 6 choose 3 over 2 possibilities here. Or is that, I think, 5 choose 2 possibilities, if I'm not mistaken, because if the first one is an A, then I have 5 choose 2 ways to look at all the other ones. So that is 10 options, and here I've enumerated them. And I think I have, at least. And all of them, like, work. So now I'm thinking that, and if I enumerate for 4, it will also work. So my solution set is changing. Why is that? Can you find that out? Can you figure out why is it that my solution set is changing? I know that k needs to be greater than or equal to n. I'm thinking if it's equal to n, it's going to work. It's worked so far. But what do I do? Like, for 4, it also works. So let's go. Like, if you don't have an idea, and I certainly was like having some ideas, I was trying to find out which ones don't work. Why does 5 work and 6 doesn't work? What's happening there? Why is this the case? And I needed to play around with 4, which if you need to do that, I suggest you do it now. And here is n equals 4 now. And what I get is once I play around with n equals 4 and k equals 7, I saw that, okay, I thought it was just like A, B, A, B, A, B, A, B, A, B, A, B. That doesn't end up working. But wait, for 7, if I have 2 A's and 2 B's, 2 A's, 2 B's, again, it doesn't work. What is the reason this isn't working out? And what is the reason that this thing always seems to be working out no matter what I put at it? And I'm thinking, okay, so it seems like 4, 4, 4, 5, 4, 6 are working, but 4, 7 isn't? Like, what's up with this? Why is this the case? And the 7, like if you stop and think about it, well, what's really happening here is that at every point, like I have the same chains. There's no new chains being formed. I mean, there's no larger chains being formed. There's another way to look at it. So that is what I'm having here. I'm always going to have 4 chains of size 2. 2 for A, 2 for B, all of size 2. That's what I'm having here. And here, like look, I have 4 chains of size 1 for both A and B. And then here, in the next step, once I move this, I get how many? I get a chain of size 2, 1, 2, 3, 4, 5, 6 chains of size 1. Okay? So I have, let's write that down, like 8 size 1. And here I have 6 of size 1 and 1 of size 2. And then here, what happens when I move these? They don't form a new chain. This one does. I get now, what's it called? 1, 2, 3, 4. 4 chains of size 1 and 2 chains of size 2. Okay? And now here, what am I getting? I'm getting how many chains of size I'm getting? So I'm moving the A here. I'm going to get a chain of size 3 now. So I'm moving the A to the back. I'm going to have 1. Okay, let's see how many chains of size 1. 1, 2. 2 chains of size 1 and 3 chains of size 3. Actually, no, 2 chains of size 3 and 0 chains of size 2. Okay? Now, what happens when I move here is that, okay, nothing really changes. I get 2 chains of size 1, 0 chains of size 2, and 2 chains of size 3. And now here, because I'm moving these A outside and now combining the B's together, what am I getting? And here, why didn't I have a new chain? Like this is us trying to figure out what is it that's happening here? Why is it that something is succeeding and another thing is failing? What is happening with these chains? So here, what I'm getting is, this is getting to this side, so I get one chain of size 3, one chain of size 1. So I get one chain of size 1, 0 of size 2, and then one chain of size 3, and one chain of size 4. So look at it, what it is I'm getting. I keep increasing these chains, not these chains. I get now 0, 0, 0 size 3, and 2 of size 4. And I continue with that. How am I going to think about this, deal with this? Whereas this here, I keep getting the same number of chains. Sometimes they stay the same, sometimes they increase, and they're increasing till 4 and 4, like only 2 chains of size 4. So, or 2 chains of size n. What do you think the solution may be? Do you think that there might be a way that you can generalize this thing that's happening for 7, n equals 4, and k equals 7? Pause for 10 minutes and try to generalize that part right now. And here's what the idea is. So the idea really is, okay, I'm not getting any new chains aren't getting formed with k equals 7. You can also try this thing out with k equals 9 and n equals 5, right? Because for 5, what we'll see is that at 8, it doesn't end up working, but it's like so close to where like we stay at the same number of chains at 2 turns, and then bam, no more chains of the same size. It's kind of sad. So then 5, 8, these are the ones that always bring us down to 4, 4. Okay, so what do we have now? Like, how do we think about this in general? Well, it seems like there's an odds and evens thing here that's happening, right? We need odd, even, odd, even, odd, even, and then we get, like if we go from an odd to an even, we get the same number. From an even to an odd, we get another one. Okay, so it's something to do with these floors and the ceilings of these numbers, and what you get is if I have a bunch of A's, I have, say, k A's, then I have k B's, and then I have L A's, and I have L B's. If, say, k is greater than or equal to L, right? And k plus L is equal to Rn. If, actually not k, k is already used. Let's say x and L, right? X and L, not usually the ones that are used together, x and L. So now what is happening? If, like what is the last place here? The last place here is 2n plus 1 minus L. That's the leftmost place here. So if 2n plus 1 minus L is greater than or equal to k, then we're going to be good. Like we're going to be able to then go from here to ax, bx, al, bl. And then we're going to go to al, bl, ax, bx, and then bx, al, bl, ax, and then from there, we're gonna go back to the top, okay? So that's what's happening like in general now. If we get these leftmost couple of ones, if we get them all to be the same, we can continue making the chain, because what is creating new chains? What's creating new chains is that if on the kth position is an x, the fact that there's a y to its right, like if k is now greater than or equal to n, the fact that there's a y to its right means there has to be a y to its left. Like it has to. And someplace we can't have, we would need to have k minus 1, so k x is here. If k is equal to n, that's done. If k is greater than n, that's impossible. We have at most n x's, where x is either a or b. So, and if we have a chain here with x's, they end on the boundaries with some y's. Once we take them to the other side, a new chain gets formed. A bigger chain gets formed. Like one gets destroyed, one gets formed. And how do we want to think about this formation destruction of chains is the next part. But this part is to say, wait a second. So if I set, like, what do I need to, like, what does this make k? Like, which k's don't work in this case? So x greater than or equal to 12, but we want to have them to be like as close as possible to one another. What do we set to make this the most general possible? Well, we set x to be equal to the ceiling of n over 2, L to be equal to the floor of n over 2. We can also, play around with this on the evens and odds case, right? And we get a sense of what this is. X plus L is equal to n. Again, casework, you can check that out. Now, this means that if 2n plus 1 minus L is greater than or equal to k, so minus the floor of n over 2, which is equal to the ceiling of n over 2 plus n plus 1, if this thing needs to be so greater than or equal to k. So what does this tell us? Well, it means that if k is actually, my bad here, this was supposed to be less than or equal to k and less than or equal to k because I want k to be, I want to take this to the other side, right? I need k to be over here, so I need k to be greater than or equal to the leftmost part of B. So k needs to be greater than or equal to this. In other words, we have a greater than or equal to sign in both of these cases. And what does this mean? It means that if k is greater than or equal to this thing over here, so this thing is, so if k is greater than or equal to n plus the ceiling of n over 2 plus 1, then we have an initial ordering of these coins such that we get into an infinite cycle. In other words, we never get to n of these of the same kind that are all on the left, right? That's what it means. So k can't be greater than or equal to this, and it can't be less than n if this is to always work. Now the hypothesis and playing around with small numbers, we get that k is less than or equal to n plus the ceiling of n over 2 and greater than or equal to n, that it's between these two numbers. This is our hypothesis now, and we need to prove it somehow. How do we do that? Well, this is the part where we're trying to formalize these things. And there's many ways we can go about doing that. I invite you here, pause for 5 minutes, think about the formalization of this chaining thing that's happening, right? And here's what's happening. So what we have here is we're having chains of size 1, then of size 2, and okay, how do I show that I will continue creating bigger chains if something is changing, that I'll never have smaller chains? How can I formalize that? My first initial thought was, okay, it's some sort of function. Let's say that Ci is the number of chains, length I chains. And let's look at the function 2 to the I to the power of Ci. This is sort of how I thought would have the property, I haven't checked it, the property that if I and j are lost, if I lose I and j, so if I have Ci minus 1 times I plus 2 to the j times Cj minus 1, that if I lose one, but on the other hand, if I add a chain of size I plus j, Ci plus j plus 1, that this will behave nicely to me. In other words, that I'll have some upper bound on the number of chains and that I'll have a strictly increasing function or a strictly decreasing one. But I was betting on a strictly increasing function. That's one way to look at it. Another way to look at it is, okay, let me just look at numbers in base n, in base 2n actually. And let's say that, 0 is the so if I have an n-digit number in base 2n, so this is number x1, x2, xn, this is in base 2n. And what do? Xi is the number of chains of length I. Initially, this is what's it called? 2n, 0, 0, 0. At each point, this number keeps decreasing. And, right, that's what happens at each step. Like you take xj and xi are decreased by 1, and xi plus j is increased by 1, or it remains the same. At some point, this number it can't decrease forever. It has a minimum, which is 0, 0, 0s, and 2. That's its minimum. And we also have like nice property here that the sum of these xi, it's not actually a super nice property. It's the sum, what's it called? xi times I is equal to 2n. That's the property of this thing. And we could, also say this has a minimum. Like these are the monovariants that I first initially thought about. However, there's a much simpler monovariant here. Can you see it? It is that the total number of chains keeps decreasing or remains the same. We have 8 chains, 7, 6, 4 chains here, and then 4 chains again, 3 chains here, and then 2 chains here. Now, it doesn't always have to be like that. Here we always have 4 chains. So at some point we need to have this point of stability, right? That it doesn't go down any longer. It's an infinite process. It can't always go down forever. So at some point it needs to stay where it is for good. So at this point, let's say we've reached that point. Now, what does that mean? That means that whenever we do this operation, now we're assuming that k is between n and n plus the ceiling of n over 2, means that whenever we do this operation, and we also just want to check out that, okay, so for 3, this ends up being k is between 3 and 3 over 2. The ceiling of that is 2, so 3 plus 2 is 5. Oh, okay, great. That's where the boundary should be. We are good. We just want to check that out. And now what we see is, okay, so in general, what I'm going to be having is, let me clear this board up a bit. What I'm going to be having is actually this. Now, I'm going to have some chain of A's, let's say LA's, or let's say X1A's, then Y1B's, then what's it called? X2A's, then Y2B's, and so on and so forth. And then if I'm ending with an A, mind you, if I'm ending with A, X to the sun T, X, so say there's D A's, I'm ending with an A, what'll happen? I'm assuming X1 is less than N. Okay, so some of these numbers will now, some of these chains will now move to the end. If it's a chain with an A, I'm going to get a new chain. I'm going to get less chains. That's a contradiction. If it's a chain with a B that's inside here, then once I move it, so if I have a chain B xi, I have A xi plus 1, B actually yi A xi. If I move this out, I'm going to get one less chain here. So I need to end with a B xt. Okay, great. And now what'll happen? I'll always need to have that the last one needs to move to the back. So this one, this chain needs to move to the back. Otherwise, it's like a contradiction to my assumption, which is a valid one. I mean, not a contradiction to my assumption, but yeah, I mean, actually, do I want to call it that? I don't know. You tell me, what should I call this, actually? So what do I have now? I'm going to have now B xt, A x1, B x1, all the way till A xt. And now this one is going to move back, and we're going to have A xt, B xt, and what is going to happen here, this is now A xt minus 1, B xt minus 1, right? What's going to happen here is that all of them are going to go through until we get A2, B2, A3, B3, all the way till AX2, x, x2, by1, y. Sometimes, you just like forget how you've actually, and this is by1. You forget the notation you've used. And then we're going to go back here. So at some point, we're going to get the smallest chain on the end, right? That's what we're saying. We're going to get the smallest chain on the end. So if t is greater than or equal to 2, what do we have? Well, we have the sum of the xi's, x1 plus x2 plus xt is equal to n. Well, if the minimum one here, without any loss of generality, is x1 is the minimum of xi, then this is greater than or equal to t times x1. If t is greater than or equal to 2, this is greater than or equal to 2x1. In other words, the smallest chain is less than or equal to n over 2. Because we're in the integers, this is less than or equal to the floor of n over 2. Right, the odds case gives us this. So now if xi is less than or equal to the floor of n over 2, what is on the leftmost position? Like, to have this be the case, we need to have that 2n plus 1 minus xi for every single I. This is the leftmost one. It needs to include k. So k needs to be bigger than or equal to this. So k needs to be bigger than or equal to this. Right? And now let's get to our contradiction. So if this is true, then minus xi is greater than or equal to this. Now this is greater than or equal to 2n plus 1 minus the floor of n over 2, which is equal to n plus 1 plus the ceiling of n over 2. But we've said that k is less than or equal to n plus, k is less than or equal to n plus the ceiling of n over 2. And this thing right here is a contradiction. So our assumption that we could be doing this forever has led us to a contradiction. In other words, t cannot be greater than or equal to 2. In other words, it has to be 1 at this final point. And then we are done, because then if t is equal to 1, then we have n a's followed by n b's. And then they'll switch around forever. And this finishes up our problem. I really like this combinatorics problem because it's, you're just there, you're just reaching for it, and you think you have something that, like, I first thought, like, oh, it's just like A, B, A, B, A, B, A, B, A, B. That's the construction. And then you think about, wait, what is it that this actually gives me? And you're like, oh, wait a second, it's not. It's not the construction. For 4, it's not the construction. I'm missing a thing. And then you see, okay, what else is happening? Okay, so these chains, can they keep on forming forever? And that's the big idea. Can these chains form forever? And you're like, wait, no. Like, it's like somewhat of a finite process. So then you're like, okay, how do I formalize these things? What do I need to have happen? And then you're just trying to formalize it better and better and better. And that solves the problem. I hope you've enjoyed this. And as always, thanks for problem solving.